Hey dude, how are you?
Good. How are you?
Very good, thank you. So you are the bravest group member because you are coming to the school.
Yeah, I'm in Dunbar right now.
I see it from the environment. Okay. Congratulations. Is there a
No,
noise? Is there a noise because of construction?
Yeah, it's a bit of noise, and because of that, when they're doing these pilings, I haven't been coming in because it's annoying. But I have much better internet connection here than I do in my apartment.
Okay.
No, the reason I started coming in is I was feeling really depressed, and this has been helping with that.
Okay.
So that's why I've been coming in. But
so, do you get any payment for the summer?
I got an assist contract earlier today.
Congratulations. Okay.
So I have no idea what I'm doing. It was vague to the point that I could literally be doing anything. But I got a contract earlier today.
This is great. Congratulations. I cannot brag that I became terribly rich, but soon there will be opportunities to give maybe not full support, but a little bit here and there. So some grants are coming through. So I'm not telling you like count on me, but something will be possible.
I had assumed I would probably be a TA my entire time here.
It's not good for excellent research project, but it is good for the career because if you decide to apply for any academic...
At the very least, I'd like to be the P-Chem TA my entire time here.
Okay. I see.
I don't mind dropping the Gen Chem.
So you interact with Uwe on P-Chem lab?
What was that?
You support class by Dr. Burkhaus, Uwe.
Yeah, that was odd last couple of weeks of that class.
I see. How are you, Ivan?
Good afternoon.
How are you?
Good, how are you?
Very good. There is a call to attract tribal students for very brief, like 2 weeks research projects. And I will need to make a PowerPoint quickly describing what our group is doing. So I will look around and maybe I will ask a little help. So it should be very simple and visual for non-professionals. Some other groups are just taking cell phone, walking around their labs, telling some words like here is the instrument and just sending it out. David, I will try to flip the slides myself, but since you are in the best connection spot, maybe if there will be delays, then you like take the control from me and flip your slides when it will be your time.
Okay.
You know how to share screen this connection, right? It's not a, how to share screen. So at the bottom of your hello, Aaron. How are you?
Good, Dimitri.
Well, at the bottom of this communication software, there are like symbol of microphone, symbol of camera, symbol of phone, and then a symbol of display. So if one clicks on display, then control goes to you, and anything that is on your screen is shared.
Yeah, I'm looking at it right now. It looks like I have to quit the program for a second, though.
Okay, it may not be needed immediately, but just prepare that in the middle it could be possible. Okay, yeah, excellent.
I think I figured it out.
It was very quick. It was very quick. Someone was taking a screenshot. Oh, hi, Javed. Thank you for joining.
Oh, thank you. You're welcome.
So we are waiting until for Salim to connect. So it would be very interesting to hear from him, and there are slides, as you have seen. Oh, hello, Salim. Thank you for joining. If you speak something, can we hear you? Can you just tell some? Okay, very
yes.
good.
Okay.
That's super. That's super. Oh, hello, Fatima. Nice seeing you connected. So let's plan on. We will start in few minutes, seconds. When first we will have two presenters, Salim and David, and when presenters are presenting, maybe the rest of us should turn microphones off, and when there will be questions and answers session, you can turn them back in. The goal of today's presentation, I don't know if Salim, do you know if Dr. Hobby will connect?
I'm not sure, to be honest. He's not at the lab today.
Okay, well, maybe he would join later from home, or we can share recordings. So there are experimental efforts at Dr. Hobby lab, and Salim and Aaron both contribute to this effort in characterizing optical properties of perovskite quantum dots. And in experimental modeling offers several challenges to computational modeling. So in order to understand what is going on in experiment, one needs to run several experiments and address some challenges. So we will have two presenters. First is Salim. He will exactly touch the right point of optical properties of transition metal manganese dopant and its optical properties. And the second speaker will be David, who will explain a little bit more about host material. What happens if one does not dope the same system or optical signatures, and we can compare and get some insights. Also, Aaron is not showing slides, as I understand, but Aaron is very much welcome to give some comments, and maybe you can even tell a couple of words right now, repeating something that you were telling a couple of group meetings ago, like how do you see challenges appearing in experiment? What is not what is not clear on experimental side, and where computational modeling can contribute?
I'm working on some slides now. Just a couple.
Okay.
So those should be ready. I by the time my turn comes.
Okay. So then you summarize effort and especially focus on experimental demand, right?
Mm-hmm.
Okay, very good. And yeah, please send them to me and be ready also to take the control and present on through your sharing of screen. Okay, then let me suggest that Salim will start, and unless we find challenges in presentation, I think I will try to swap slides, but if it will go slow, Salim, you can take control over and share your screen. But right now, I think your slides are on the screen and you are welcome to start your presentation. Salim, we do not hear you. Can you switch your microphone on?
Oh yeah, sorry, I forgot to turn it on. Yeah, sorry.
So please start over.
Okay, so yeah, thank you and hello everyone. My name is Salim, and today I'm going to present. I'm going to talk a little bit about the emission from manganese doped lead halide perovskite quantum dots, and touch touch a little bit two concepts. One of crystal field splitting, and the other one about spin orbit coupling. So next slide, please. Okay. Perovskite quantum dots are quantum dots having the structure shown in the figure at the top right. And this crystal structure is dependent on the ionic radii, and they have a formula of ABX3, where A is the organic cation, B is the metal cation, and X is the halide anion. So they're very much used right now, and people are really interested in them because of their good optoelectronic properties. They have good photoluminescence, and they can be used in application. I mean, they have a lot of applications for LEDs and solar cells. So they also offer a high degree of tunability by mixing the halide anions, and that will change the band gap as well. But they're still unstable to moisture, and this instability is maybe caused. I think is caused also by the dynamics of the ligands, and yes, by the dynamics of the ligands and the atoms that it's attached to, because of maybe its ionic because it's ionic bonding, I guess, between the ligands and the atoms. And so one way to be able to stabilize them is to change the atomic radius, because I've read that atomic radius can also affect how stable they are. So, and also to use dopants. And one good example of a dopant that can be used is manganese. And that manganese is able to make it stable, and also change the PL to around 600 nanometer, like in the figure to the bottom right shows. Next slide, please. So manganese is a transition metal ion having 5 unpaired valence electrons in the d orbital, and these orbitals have these shapes, or these lobes that we see at the figure to the top. And That's the one. The manganese ion is in vacuum, or is just by itself. But in the lattice, in the perovskite lattice, these so we have halide anions, which are the ligands attached to the manganese atom on these axes that are shown in the orbital pictures. And because of its symmetry and because of how close or far it is from the lobes of the orbitals, and the fact that they have a negative charge, they are considered as point charges and create this Coulombic environment with the lobes of the orbitals, and these would allow for energies to be higher, and for the groups of the electrons in the for groups of the valence electrons to be split into two groups. And these two groups depend also on the lobes, on like how the lobes look like on the, like, regarding the, like, depending on where the ligands are at. So we will have two of them that have higher energies, and three of them that have lower energies, like shown in the figure at the right.
You mind if I ask a question?
Yes, sure.
So you say halides surround the manganese?
Yes.
So are halides strong splitters or weak splitters? Like, how strong is the Coulomb?
Is the Coulomb interaction?
Mm-hmm.
I believe the Coulomb interaction, how strong it is depends on depend on the shape of the lobes. For example, if you see that dz squared, that one is definitely aligned with where the ligands will be placed. So that one will have stronger Coulombic interaction, and that would make the splitting to be at higher energy than, for example, the ones where they are not aligned with the halide anions or the point charges. Or you mean like overall? Overall, I think they have stronger energy than other type of crystal ligand field, like splitting. For example, like it has higher energy than the tetrahedral split. I'm not sure if that answers the question.
Well, if you speak to a chemist, they have like a series of like how strong an atom or molecule is as a splitter. So halides generally fall into the weak field. So that's that delta 0 on the very right side of your figure.
Yes.
So that would be like a small value for halides.
Oh. In this case, then the tetrahedral one has even smaller value than this then. I'm having a presentation.
Generally, tetrahedral has smaller than octahedral splitting. And in addition, tetrahedral, they split opposite. So tetrahedral has 2 on the bottom and 3 on top.
Yes. Yes, I knew that one, but I didn't know that in general, even the octahedral split would be considered as low splitting energy.
So yeah, the energy can get small enough that you can start filling up the second shell before you completely fill up the 3 lower ones. It's actually, I don't honestly know much about manganese chemistry, so I'm not sure about it, but that is possible.
In this case, they're high spin. So
okay.
So yeah, then the splitting is small enough that you fill things together.
And would this one be considered as a small enough as small enough energy to do that, to be able to act like that?
So if it,
yeah, so experimentally they see that you have 5 upspins. So that means that this energy splitting is small. compared to thermal energy.
So if I understand, in which conditions then would we have definitely this split, and the octahedral or tetrahedral split in the case of manganese in the perovskite?
Let me contribute. I think Aaron and David were focusing on not on the spatial arrangement of the ligands, but on the strengths of ligand. Like, what if one replaces iodine with bromine, with chlorine, or with nitrogen, or oxygen? So different elements used as a ligands provide different value of delta zero splitting.
Oh, okay. I see. But I think bromine, the Br, has even lower, right, than chlorine, and iodine has a little bit higher. Isn't it correct or no? Because I'm not sure if that one is related to how when we change the halide anion, how it can.
So
redshift.
the strength is changed from the top to bottom. Maybe the chlorine is a maximum in halide group, so iodine is a minimum in the range.
So that would depend, and if you look at the periodic table, how does it depend on the electronegativity?
I think if I remember, it depends on both the electronegativity and the size.
And the size, okay.
So the radius.
Because chlorine would have a higher, I guess, electronegativity, and would be, I'm not sure about the size, but okay.
It's related with the charge density, because both iodine and chlorine both has a one negatively charge.
Yes.
But the chlorine is a smaller ion, so it has a higher charge density. So it has a more stronger, I would say, Coulombic effect. That's kind of thing, yeah.
Okay.
In a very broad sense, yeah. So.
Okay. So even though it has strong interaction, it would still be considered as weak, like Aaron mentioned earlier.
Yeah, so it's weak in the sense that it's not like this delta zero is small enough that this takes a high spin. So you have 5 electrons. They can either have 5 up spins or one.
Yes, I know that they're supposed to be at 5 up spins, right? 5 alpha spins if in vacuum. So the energy, because I'm not sure I understand what Aaron you just explained. If they have originally they're supposed to have 5 up spins in vacuum, and so in the perovskite lattice, so you're saying that the chlorine ions have not such a high Coulombic interactions to have have this 100% like split, or this split is like not high enough that you can.
So
like,
delta O
differentiate
is smaller than KT here.
Okay.
So there's a population. It's going to fill the higher one with an up spins before it starts filling the lower one with down spins. So instead of having three up spins and 2 down spins, you're going to have 5 up spins. Does that make sense?
So we're going to have 5 up spins.
So you're going to put an electron in each orbital.
Yes.
Even though they're split, before you start filling up, putting a second electron in the bottom 3.
Okay. So you start filling the ones on top first, and how do we end up getting 5 alpha electrons again? Even though after split you said we have to fill from top.
So you start filling from the bottom. You fill the 3 ones on the bottom.
Yes.
And then that was small, you then start filling the two on the top before you start filling the second electron on the bottom. If delta O was big, you would fill the 3 on the bottom, and then you would put the second electron on the 3 on the bottom. But
Oh,
because
I
it's
see.
small,
It makes sense. It makes sense now. Okay. Yes. Okay. Yes, that makes sense now. So should I continue or should?
Yes, please continue.
Okay.
And
okay.
Just a quick comment to the question you said before we got on that little tangent. The splitting, how they split is based on the orientation. So whenever it gets an octahedral, it's going to have that orientation. The difference between the levels is going to be different, but the orientation itself is going to be the same. And there's different splittings for different orientations for all.
Right.
All
so on the lobes of the orbitals, right? And
so
where
yeah,
the ligands are.
Job explaining which ones are the high ones
So the high ones would be the ones that are like directly facing or close to where the ligands are, right?
So yeah, that's what it is in this case.
Right. Okay. That makes sense. Okay. So also, so about the second concept, so when upon excitation, it happens that the electrons revolving around the nucleus creates that the electron can create a magnetic field, which also interacts with its intrinsic spin and allow the electron to flip. And that's called the spin-orbit coupling. And that could also allow the change of the PL. Next slide, please. Okay, so the models used, so we used the 88 atoms model, including, so in here, our A here is the amine propane, C3H10N2, and the middle cation was lead, and also one of them was for the dope model. One of the leads replaced by manganese, and so the halide ions are chlorine here. And here you can see the videos. In the video, the first one that's playing, we can see like what the model looks like. And here, like I mentioned earlier, I think the interactions between the atoms here are ionic, not they're not having a covalent bonds. Yes. So yeah, in the second video, so in the first one it's just a rotation of the model, but in the second video it's a simulation of molecular dynamics at 300 degrees Kelvin. And so here energy, the data that was extracted were energy minimization, the density of states, partial charge densities, and the PL spectrum. For the doped model, using spin-polarized density functional theory and non-collinear spin density functional theory, and also molecular dynamics PL spectrum was plotted for the doped model as well. And PB and also yes, the PB exchange correlation functional was used with the PAW pseudo potentials and using also the plane wave basis set. Next slide, please. Okay, so computational methods for the spin-polarized density functional theories, we use the Kohn-Sham equation where here where it's explained like where the electron orbitals, the orbital energies, the alpha and beta spin components, the position R describes the position of ions and the smaller position of electrons, and the electron densities as well. And here the first term corresponds to the kinetic energy with the gradient symbol as well. So this Kohn-Sham equation is combined with the occupation. No. The orbitals are combined with the occupation functions, and the equation in the middle shows the total density of electrons. So that's just with just a combination of the occupation function and the electron orbitals. So the partial charge densities were obtained by using the equation shown at the third point. And to account for the changes of in occupation, we used the density matrix as the first one that I showed. The E total is equals to E total and rho alpha, rho beta, and extract the functional derivatives. Please, if I'm not correct anywhere, just you can stop me, or because I'm not. So the functional derivatives were extracted, right? Those are no. Yes. We have two functional derivatives, right? Which are the two last equations shown in this slide. So next one.
Salim?
Yes.
The one word that you can add to this slide is self-consistency. So the V sub alpha and V sub beta symbols from your last line are recursively added to the first equation, which has V sub sigma. And they are like solved in a connected way.
Okay.
Okay. Let's go.
So recursive. Okay.
Let's go to the next slide then.
Okay. So for the non-collinear spin, so the Hamiltonian for the spin-orbit coupling is considered as a perturbation for the Kohn-Sham equation. So it's just an extra term, I guess, for like added to the Kohn-Sham equation. And it's also approximated to be the second equation, or yes, the second equation shown here in this slide. I think I should note them too. I should have 1, 2, 3. Okay. And yes, it's also approximated to be and used actually to be the equation in the second line. So in the third line, from that equation, there is the symbol for V sphere, which corresponds to the spherical part of the mechanic potential, and L the angular momentum, and M angular momentum, and S the spin matrices. So from so the Hamiltonian from the density functional theory is also equals to the Hamiltonian from I forgot the name of the SR, when the Yes. It says SR. When SR, all electron block PAW potentials are applied, then the Hamiltonian from the density functional theory can be represented as the Hamiltonian from SR. And the Hamiltonian will just become the Hamiltonian from the relativistic Hamiltonian will be represented as the Hamiltonian from SR plus the Hamiltonian from spin orbit coupling. So then here the electron density is defined as the matrix shown in the fourth point, where each of the components are described as the equation. Let's just by it. So we can have 4 of them. This is just for alpha beta. We have alpha beta alpha and beta beta. And the total energy here is with the matrix with the
Depends on all 4 of them, right?
Yes, it depends on the 4 of them, yes. And their functional derivatives, then we're going to have 4 of them instead of the 2 of them that we had in the spin polarized DFT. We're going to have 4 functional derivatives that are calculated and then introduced back to the main equation.
Mm-hmm.
Next slide, please. So after these computations were done, then the first thing that was obtained was the energies of the orbitals with the band numbers and the occupations for the undoped model, the doped model at the ground state, the doped model of at the excited state, and also using the non-collinear spin DFT. So in here, in the first table, we can see that the band numbers and the energies look about the same for spin alpha and spin beta, and the occupations also are the same. So that would be translated into a symmetric alpha and beta density of states. And this, and also we can also, I can hear myself talk.
I think if everyone except Salim switches off microphones, then this background will disappear.
Is it okay now? Oh, yes, it is okay now. And also from the first data table, we can also predict what the PL would be after excitation. That would just be the band gap or the energy difference between the HOMO and LUMO orbitals, right? Yes. So, and if we do that, for example, for alpha, we see that the difference between HOMO alpha and LUMO alpha are about 3.5 electron volts, which correspond to a photoluminescence of about 350 to around 400 nanometer, which can experimentally be proven to be true, and it was seen to be true during experiments with Aaron. So for the dope model, at the ground state, we can see. So the first thing that we see from the occupation column is that we have 5 extra electrons in the alpha orbital, that are spin alpha, that are not spin beta. So these orbitals would be attributed to the manganese, to the contribution of the manganese unpaired electrons. So that would be described as a density of state that's not symmetric, and also the crystal field theory also predicts that these 5 electrons contributed by the manganese would have higher energy than they were supposed to have if they're not in the lab, and these higher are here in this table. Well, I'm not sure if I can say that it's predicted to be there, because I'm not sure if, I mean, I know experimentally, well, it is, and the results will show that it is, that it's the contribution from these, from the manganese electrons or ampere electrons in the d orbitals. But I'm not sure if just from this crystal field splitting that we can predict, or that we can say that, okay, since there is these electrons are going to be the closest to the like to the HOMO and LUMO. Okay, so for the doped model, for the doped model at the excited state, we used N up down, which is the difference between the number of alpha and beta electrons. We chose this number to be 3, just to allow this crystal field splitting to be to allow for the spin orbit coupling to kind of be not accounted for, but to kind of force it to be, to give the or to show us something that we could maybe understand or predict that would happen without actually doing the computations with the spin orbit, like accounting for the spin orbit coupling. And in here, so yes, okay, so yes.
So you just artificially promote one electron from alpha manifold to beta manifold, right?
Yes.
So you take electron from alpha orbital 136 and place it into beta orbital 132.
Yes.
Okay.
So that one is not really like 100% accounting for the concept itself of the spin orbit coupling, but we kind of force the system to behave that way to see, or to see if, you know, to predict or to see if it's going to give something. And in the last table, this is the band numbers and energies and occupations for the non-collinear spin DFT. So that one accounts for the spin orbit coupling. It is allowed in this case. And here the occupations, instead of being 2, I mean, instead of being, instead of being separated into alpha and beta orbitals, they're just like, whether they're just present or not present. It's just, and that's because the spin acquires two parameters, which for in the case of spin alpha, the parameter for spin alpha would be 1, and then the parameter for spin beta would be 0. And in the case of beta, it would be the opposite. But then in this case, they are also allowed to contribute maybe at 25%, 75%, since it's a vector. And so the square root of the addition of the squares of these two parameters would give 1 if there is an electron and 0 if there is no electron. So in this case, we just have alpha, we just have not alpha, we just have HOMO and LUMO and HOMO orbitals or LUMO orbitals. So next slide, please. So about the graphs for the undoped model, like I said before, we would see the symmetry along the x-axis. So we can see that symmetry as well. And to the left, we have valence band, to the right, conduction band. And so besides that, we can see also the band gap, like we said before, like the data table showed us, it would be around 3.5. That would correspond to a PL about 350. And also at the HOMO and LUMO, we also looked at the partial charge densities to look at the orbitals. And so we can see that the orbitals at HOMO, not sure if I included them here. They are localized on at HOMO. Yes, at HOMO they are localized at the chlorine, and they look like two p orbitals. And then at LUMO they're localized at the lead, and they are p orbitals as well, but different p orbitals than the ones at the chlorine. Next slide, please. So for the doped model at the ground states, like we said before, we're not going to see any symmetry, and so occupation for alpha different than occupation for beta, energies for alpha different than energies for beta, and we can see two extra mountains, I guess, in the alpha part of the orbitals that are absent in the betas, and that would be the ones the extra electrons that we had, the 5 extra electrons that we have in the alpha orbitals that are not in the beta orbitals, the ones contributed from the manganese. And so besides that, the HOMO alpha, the difference between the HOMO alpha and the LUMO alpha is about the same as the undoped model, but if we consider, or if we allow this electron, for example, to have a transition from the HOMO alpha to LUMO beta, then the difference between these two energies would be about 2 to 2.5, something like that, and that would predict a PL of at least 500 to 600 nanometers. And so if we look at the the orbitals as well, we can see that the orbitals from HOMO alpha -4 to HOMO alpha are look like the d orbitals from manganese that I showed in the earlier 2 or 3 slides, and that the LUMO from LUMO beta to LUMO beta +4 as well are the ones from the manganese atom or ion. But then after that, as we go a little bit further, we can see that the LUMO beta +5 is the one on lead, is the p orbitals, the 6 p orbitals from lead. So this way we know that for sure the electrons, the extra or the extra lobes that we have that at higher energy in the LUM in the HOMO are the ones contributed from the manganese ion. And so, like I said earlier, that we will have a PL of about 500 to 600 nanometer. And here we have the spectrum plotted from the data obtained from these calculations, from the spin-polarized calculations. We can see the peak around 500. We can see also the first peak around maybe 300. So, so that would be expected from the two different types of transitions together. And so to the right of that spectrum, we have the one obtained experimentally, where we can see these two peaks as well, one around 400 and the other one around 600 nanometer. Next slide, please. So for the non-collinear spin DFT of the same doped model, we don't have alpha or beta orbital spins like I mentioned earlier. So we're only going to have just orbitals. And here we can also look at the energies of these orbitals and identify where they are on the density of states, and also look at the orbital and confirm they are orbitals from, like they are localized, where they are localized, and so we would understand the transition, right, between HOMO and LUMO, I guess, and which one and which ion contributes to this transition. So we can see from HOMO -4 to HOMO that these, from the orbitals at the top of this density of state, that they are localized on the four last ones are localized on the manganese and look like the orbitals that we looked at earlier. But then the one before that is the one localized at on the chlorine. That's the 2p orbital localized on the chlorine. And then also for the LUMO, we see for the LUMO on the bottom, we see that from LUMO to LUMO +4, they also have the same shapes as the one from HOMO -4 to HOMO. And that right after that, at LUMO +5, we have the orbitals localized at the lead. So that also confirms what we said earlier about the spin polarized DFT. So that says that so this result tells us that this non-collinear spin DFT, when accounting for the spin orbit coupling, gives even though we didn't actually separate we have these alpha and beta orbitals both together. We can look at them and we can identify them, and this tells us that it's a good method to use as well and account for this phenomenon that's not supposed to be able to be possible in the, I don't know if it's in the normal case or regularly. It's not. It's forbidden, right? So.
So
Yes.
So in your spectra, so all the peaks from like 500 to 2000, those are DDE.
Yes, this is the one that I truly didn't understand myself. So I obtained the spectrum from the non-collinear spin DFT with the doped model.
Mm-hmm.
And yes, I used the oscillator strength from all of the transitions that we had there, and plotted the spectrum from 150 nanometer to 3000 nanometer to see how it's going to look like. But this is what I found, and to be honest, I'm not sure if I understand this nicely. I know that the energy difference here that we have from HOMO to LUMO are about even less than 1 electron volt, which would correspond to a peak, I would say, okay, above at least 1000, right, close to maybe 1500. So I wanted to see the whole thing, but it seems like we have a higher peak around, like, I don't know, from 200 to like 400 nanometer. I mean, I still see that peak around 1500, but I don't think this one would be much relevant compared to the other ones, which look like having higher intensity or higher absorbance.
Aaron?
Yep.
Let me contribute to this discussion. So the merit of this slide and the results on this slide are qualitatively correct picture. When transitions from occupied and unoccupied manganese orbitals occur inside the band gap of the host material, of the host matrix. So this is positive. The analysis of orbitals character is also seems qualitatively correct and positive. What is what needs to be improved, what is not ideal or very far from ideal here, is quantitative values of the gaps. And there are objective reasons for that. So the results that Salim is showing are made in the cell size that corresponds to undoped model, to the same like the size of the simulation cell is kept constant. It is the same as in previous models and the same as David will show later. But ionic radius of manganese is smaller than ionic radius of lead, and substitution doping reduces pressure on the walls inside this chamber. So in order to reach equilibrium, one needs to compress to make the cell smaller and re-optimize geometry once again. And this operation has not been done at the time when Salim generated these figures and data. While if this operation is done correctly, the energies become somewhat much closer to realistic values. And one of the, I think the next slide that Salim is going to show will demonstrate the data which are done after this optimization of cell size is complete. Salim, am I correct?
Yes. Yes.
Aaron, do you buy this argument?
Mm-hmm.
Okay, good. Salim, please continue. Sorry for interrupting.
Okay. No, it's okay. So I think I'm done with this slide. So we can go for the next one. So in here we have so the computations that were done were for molecular dynamics at 300 degrees Kelvin. And so the video here shows the motion of the ions and how, and also like Dr. Killian just mentioned, I'm not sure if we can see, I'm not sure if this simulation can show us how big or how small the ionic radii are, and then how to compare them with each other. But during this simulation, the non-collinear spin computations were done at each time step for every frame, and oscillator strength were all computed, and the oscillator strength from the transitions from HOMO to LUMO only were selected and used to plot the spectrum that we see to the right, where of course like I mentioned earlier, is for every time step. So every small distance difference or bond distance difference that we have all together shows or confirms, in fact, the PL that is expected from this manganese doped lead halide perovskite nanocrystals. So I believe I'm done with this slide and ready for the conclusion. So yes, in conclusion, perovskite quantum dots are very important because they have a lot of very important optoelectronic properties, and they have huge potential in many different applications, including including LEDs, solar cells, because of their high quantum yield, high color purity, and high degree of tunability as well. So in this presentation, I discussed the geometry optimization, spin-polarized DFT, non-collinear spin DFT, to obtain the spin-polarized density of state, partial charge densities, spectrum or spectra for the doped and doped model. And we also discussed a little bit on the crystal field theory, which I forgot to mention that from the molecular dynamic video, that the manganese supposedly liking to be octahedral was shown to prefer to be in the tetrahedral coordination, and so that would translate maybe into a tetrahedral split, maybe, or maybe not, or maybe it's also because of the it could be because of the size of the ion or the ionic radius that, and also because of the ionic interactions, I guess, that they would prefer to be in that coordination. But yes, we also confirmed, we also saw the agreement between the spin polarized calculations and the non-collinear spin calculations. We saw the redshift of the PL around 600 to like even 500, let's say 500 to 700 nanometer TL. And this is comparable to experimental values obtained as well. And like Dr. Kilin just mentioned, more work could be done by changing the atomic, the cell, by changing the cell size, and possibly, I'm not sure, but maybe other things can also be maybe explored. I'm not sure. But yes, thank you for listening.
Okay, please join me in thanking Salim for a very interesting presentation.
Thank you.
So, other questions to Salim or any comments?
I got a quick question.
Aaron raised the hand first.
Okay, I guess my question would be, what would be the most impressive observable that you computed, but the main observable from all the work that you did?
The most impressive, you mean?
Yeah, the one that's like the one that would make good for like a cover journal, like a POC, like the main observable that you found, or main figure.
See, what I really liked were the orbitals. I really like the orbitals and how we can see and compare them to the ones from the manganese. But I also like the density of state, the one from the doped model, the spin polarized one. Maybe with the one with the non-collinear spin as well, or maybe even the PL. But the PL maybe be expected. I'm not sure. I enjoyed really everything. I'm not sure which one would be the main one. But I like figures. I like images. I like how they look like. Like in this slide, for example, we can see the colors, different colors. So with the orbitals, with the different colors of the atoms, and you can see where they're localized. I think it's great. I think it's amazing.
Mm-hmm. I guess my comment would be, I think the line width figure, that's the most impressive one, because it's not standard to be able to get that result.
You mean the PL?
Yeah.
Oh, really?
Mm-hmm. Just because it agrees with experiment, like experimental handbook.
Yes, it does. Yeah. Wow. Yeah, I enjoyed everything, to be honest. So another question?
David, did you have any questions?
Could you take it to the model slide quick, Dimitri?
Yes. Give me a sec.
So I'm just trying to understand what I'm seeing. How's the periodicity of this model work?
Periodicity? Well, it's just this is just a small, very small part of it. It's just You would go for. I'm not sure how to, if I can describe it as right and this, but if you take the plane, for example, where you have the where you have the three leads and the one manganese, that plane, you can see in the plane right under that one, you can see the plane with the C3H10N2 molecules. You would see how many of them? 1, 2, 3, 4, and then in the middle you would see the no. Yes. So it would be these these molecules that you would see, and then in the plane under that one again you would have the three leads and then the one manganese. So it's just goes like that, like over and over and over and over. I think this is how the perovskite structure.
Effectively no vacuum or minimal vacuum at best. Okay.
What did you say right now?
So there's either no or effectively no vacuum, is what you're saying.
Yes.
Okay.
Yes.
That was all I was trying to figure out.
Okay. I hope that was a good answer.
More questions? Javid, do you have questions?
So I'm just wondering from the David question. So does it mean it's not a quantum dot anymore?
That's basically why I was asking it. But
okay, yeah.
Because the way he described it, we're looking at a 2D material.
No. It was in 3D. It goes. Well, wait. No, it goes in.
This is basically my model, except one of the leads switched with the manganese, right?
Yes.
Okay.
Yeah.
So let me bring a context. What's the reason for this? So the experimental focus of Salim are quantum dots, which are like about 3, 4, 6 nanometers cubes of this lead halide perovskites, surrounded by organic ligands and dissolved in solution, right?
Yes.
And purified through this ultracentrifugation. If one tries to model literally these objects, the absolute value of density of states for the host material will be like 100 times higher than contribution from dopant, first, so it's hard to compare. And second, there are some unresolved issues, maybe because of the lack of quantum confinement in the computations. The orbitals of manganese are getting admixed inside the conduction band of the quantum dot. This is an effect that hasn't been resolved yet. And there was a search for minimalistic model that shows as small as possible amount of this lead halide layer to focus more on the contribution of manganese. So to keep as much as possible properties of intrinsic perovskite, but to be as small as possible. And this model seems to be the right example.
So this is not a mistake. It's just intentionally simulating that.
Javad, please start your sentence over.
Oh, okay. So I'm just saying, so that means it's simulated intentionally as a 2D to make a similarity with experimental result. Is it right, or it just?
Yes.
I mean, you made.
Yes.
So in that case, I'm just wondering, how did you optimize the unit cell?
Originally, or little adjustment upon substitutional doping?
In either case, actually, because this system doesn't look like very symmetric. That's why I'm just wondering, how did you optimize the unit cell to predict in more periodic system?
So for original optimization, I think we can wait until David presents. So okay. He was founder of this research direction, and he has some hints maybe to share. So David, prepare to answer this question to Javad. I think you re-ask it. And for fine-tuning upon substitutional doping, it is very small change of the size of the cell in X, Y, and Z, maybe by less than 1%, but it changes the strain and affects energies substantially.
Yeah.
Let's check if Fatima has questions to Salim.
I'm good.
Okay, thank you. Yvonne, do you have questions to Salim?
Not really.
Okay, yeah. Well, thank you for supporting, and let's thank Salim once again.
Thank you.
Yeah, very, very interesting. And now I'm going to switch slides to the talk by David. And I suggest we all are switching off microphones except David, and floor is yours in 10 seconds. So it will be optical properties of the same model without manganese doping. So it is foundation, reference point for all things that Salim has accomplished. Okay, David, floor is yours.
So, as Dimitri said, I'm looking at the indentation, the photoluminescence of one of my models. And if we go to the next slide. We can see the model here, and what we have here is this is a two-dimensional material. So if we have the material separated into a organic layer and the perovskite layer, which if we look at my model on the right, I have two of them together, and I've outlined the perovskite unit cell. So you can see how the unit cell fits into this model. And what I have then is I'm using diammonium diammonium propane as my organic layer, and the goal with that is to create a insulating effect for electron transport and make it a little more stable material. But we're not really focusing on that effect today. And if you could go to the next slide again. So here we're looking at the photoluminescence for the material, and this was calculated with an excitation from HOMO -5 to LUMO +10. And we see that there is a excitation around, I can not read that number. That begins around 1 picosecond at approximately 3.3 eV. And on our right here, we show the intensity. And I need to do a little work because it looks like I have some intraband interactions going on in this graph. And this, so in this pure model, we're looking at that gap of about, it's got a band gap of just had this looked up all 10 minutes ago.
Hi, David.
Yeah, what's up, Jabed?
Sorry about that to interrupt. Can you tell us what is the X and Y axis and the range of the X and Y axis?
Yeah, that's it's a little small. So the Y axis is excitation energy. It ranges from -0.5 to 4.5 eV. The bottommost peak on the intensity graph is right about at 0, and the top peak is right around 3.3. And for the blue graph, we're looking at a logarithmic time scale going from -3 to 4. And in the intensity, we're looking at logarithmic intensity scale going from -3 to 5.
Javid, are you satisfied?
I can't hear you, Jabad, if you said something.
No, I just said I'm good. I just want to get an idea about the
Yeah, I appear to have made the legend a bit small.
Mm-hmm.
May I ask?
Yeah.
So I'm asking on behalf of Salim. Where does time, it's a provocative question, I know the answer, but where does time comes from? It looks like a lot of steps are skipped between geometry and this figure. So why something is changing with time, and why you excite at one frequency and it emits at another one? I hope Salim was thinking about asking a question like that.
So the time comes in because as we work with our model, the positions change slightly during the run, so it has slightly different properties as we go along. And what was the second part?
Why exciting at specific frequency?
So why am I exciting from HOMO -5 to LUMO +10, or why if we excite X amount does it come out at Y amount?
Right. Yes. This question.
So the reason, so this one has a HOMO -5 to LUMO +10 is about 4.9 EV excitation. And the reason we're not seeing a peak at 4.9 is because it relaxes to the band gap or near the band gap. And that's where the radiative relaxation occurs. All the relaxation before that is non-radiative. And if you look at the peak, it's a little hard to see because it's quite dull, but you do see some small peaks above, or some small lines above the main line at 3.3. They're just not very intense, as you can see in the intensity graph. Does that answer your question, Salim and/or Dimitri?
I'm fine. I wonder if Salim is buying this argument. Salim, do you accept it, or you want to ask more?
I'm not sure, and I quite I understand 100%. I want to ask Aaron: is this the same as this lifetime measurements that we were doing? Or I'm not sure if it's related to the lifetime measurements we were doing. That's it to Aaron though.
That one I don't know.
It's similar, but the way that the calculations are set up, there's no population decay. If that makes sense. So it relaxes to the lowest excitation energy, but it just keeps counts for where photoluminescence would come from until the simulation stops. So it's analogous to the lifetime measurements, but it's not exactly that.
Okay, I'm not sure I understand what Sudan was explained by David. Could you repeat the explanation, please, David, if possible?
What was the question you cut off?
Maybe a little bit simple terms. On the second part, why excite at one frequency and then have a peak at another frequency, or how does that happen?
So we excited HOMO -5 to LUMO +10. So now we have a hole in the valence band, out of the way around, hole in the conduction band, and a electron roaming around. So they're going to go approach the band gap, or HOMO LUMO. So they're losing energy as they approach that, most likely to heat. Not necessarily.
The phonons?
Yes. So phonons would, yes, phonons. So when they actually reach the band gap, they have less energy. There's a less of an energy difference than what we started with. So instead of emitting at 4.9, we get an emission at 3.3 EV.
And that 3.3, is it the band gap, or?
That is the band gap. The band gap was 3.29 something.
Okay. So basically, instead of emitting at the energy difference from like HOMO -5 to LUMO +10, because it loses energy and then gets closer to the HOMO, and then the LUMO, or the electron in the hole gets closer to the HOMO and the LUMO, and then they recombine, basically emitting at that wavelength corresponding to the energy close to the band gap, right?
If I understood what you said correctly, yeah.
Okay.
I'm very happy you are having this discussion. So this finding informal way to explain things is really valuable. And I was, while listening to you, I was creating a backup, so in an oversimplified way. So the arrow up is excitation, the wavy line is releasing energy to heat, and arrow down is recombination.
Yes. Okay. Yes, that makes sense. I'm excited at the higher energy, right?
So yeah, this was excited at a higher energy.
Is that the reason why we want to excite it at the higher energy? Because
so the reason I picked these energies is I looked at my oscillator strength file and I chose the highest oscillator strength that had a excitation of greater than HOMO -4 to LUMO +4. That's the reason I chose this. A little later in my presentation, I have the exact same graphs except for the excitation that had the highest oscillator strength.
Except the excitation. Okay.
So this is not the highest. This is not the excitation with the highest.
It's not the highest, right? I see. You just chose the one that probably had like most of the oscillator strength values in to have maybe, I don't know, I guess, right? Or a lot of them, but if you use the highest, maybe, I mean, there's going to be more values, but I'm not sure how it's going to look like here. Maybe more disordered or more, I mean, smaller and maybe not very clear. But if we excite it, for example, at the highest that we can, for example, is it still going to happen the same way? Like most of them that are not close, are not exactly HOMO, for example, HOMO -10, let's say, or 20 or 30, for example, if we excite it at energies that high, are they all going to lose all of them in between HOMO -5 up until HOMO have probabilities, like high probabilities of losing energies? I mean, of course they would lose energies, right, due to phonons and thermally, and what do you think would the probability be of them recombining, I guess, and emitting at that energy that's closer to the wavelength? For example, the farther it is from the HOMO once you excite it. I'm not sure if that's a good question or not, but
so you're asking if we excite bigger, give it a bigger excitation, would we see more bands? More
if we excite, would we have more counts of recombination, for example? Because normally we're supposed to.
I lost you.
I said normally we would have more bands. Normally we would have more. Sorry, I cut the mic at the same time. But normally we would have more bands, right? But these more bands, would they also correspond to more electrons that would recombine with their holes, or not?
David, would you allow me to contribute?
Yeah.
So the wavy line, the release of heat, the release of energy into heat towards the lowest excitation happens orders of magnitude quicker than radiative recombination. So in certain limits, no matter where you excite, it will rather quick relax to the homolumo and then live there long enough time for nanoseconds and slowly emit light. So this release of excess electronic energy into phonons happens of the order of picoseconds, and emission happens of the order of nanoseconds or even longer. So they are like 3 orders of magnitude different, and the little details of relaxation are not much affecting the photoluminescence.
Okay, I understand. And that means that there will be probably more recombination the more we excite at higher energy then. Because anyway, it will happen in order of picoseconds.
When you excite at higher energy, you are correct. There, like strictly, there will be more channels for radiative recombination. But there is no time to launch them, because instead of recombining radiatively, it will quickly relax to homolumo. So it's the channel of relaxation is quicker, more intense, and more preferred than radiative emission.
Okay. Yes, that makes sense. Thank you.
David, I think we all are happy with discussion. Please go ahead in presenting.
Okay. So as Levi was mentioning in the chat here, there doesn't appear to be any emissions in the low end of the range, which is in the 0 to 1.5 EV and the range in the intensity. We don't, in the intensity, the time integrated graph. We don't seem to see that in the other graph. I do not know why we don't see that there. I was wondering that when I made the graphs, but I haven't had a chance to try and figure it out.
Okay, let me contribute.
Sure.
Or anyone else wanted to contribute?
I guess my thought is the figure on the left, it's made by maximum and minimum values. So your yellow line just might be much more intense than all the other transitions. So that's why the other ones don't have in contrast. So it might be in there, but there's the shading of blue isn't enough to distinguish them.
Okay.
Yeah, I agree.
So you can simply just try like other color combinations.
Sure, I can attempt that.
Or maybe try contour plot that will draw, instead of continuous color map, it will create iso contour lines around areas of higher intensity and lower intensity. And then it will pick up small features. So this representing intensity with a color code is not ideal, and it picks only major contributions.
Okay. So, was there any more questions on this slide?
It looks like Levi asking something else in the chat line.
Wait, the color monochromaticity increases. It does not show the actual value during the time.
Blue corresponds to 0, orange corresponds to maximal value. And then it continuously scans all colors between. But the color map is the same.
Okay.
So I guess the question I'm asking is, when you plot this, does the color stay constant if the value increases at a moment of time, and then later on, if it goes down, does the color not change?
Color stays constant.
Okay. You can give yourself an answer.
I see the little confusion from this figure. So Levi is asking why right panel shows infrared features and left panel doesn't show these infrared features. And there is another aspect of this. So when one practices the equation on the right bottom, the integration of time-resolved emission into time-independent, the time steps along this log scale change drastically. And there are non-equivalent contributions from grid points at the beginning of trajectory and grid points at the end of trajectory. And some small contributions may not be seen in this color map, but due to this different time step between grid points, they are getting enhanced.
Okay.
Levi, are you more or less satisfied? Okay, he answered that he sounds good. Okay, David, please continue.
Okay, then the next slide. Where is my mouse? So here we're looking at the molecular dynamics photoluminescence, which is the photoluminescence along the trajectory for the HOMO-LUMO gap. And compared to selenium, where the doping showed up at around 650 or so EV, or not EV, nanometers. It's out very smoothly right around 3.2 EV, which equates to about 380 nanometers. And as this was
I have a question. Was it for your doped model or for your?
So I don't have any doped models. This is pure
okay.
lead. So from the sound of it, you took my model and switched one of the leads for manganese.
Right. I see. I see. Yes.
It's pure lead. So this would be undoped.
Okay. Yeah, it makes sense to have the energy around 3.2.
3.2, 3.3. The value ranged along the trajectory from 2.9 up to about 3.5, mm-hmm. But the peak was around 3.2.
Mm-hmm. Okay.
So what would be your expectations for the line width? Would you expect it to be narrow? So do you expect the line width to be narrow or to be broad? Like Salim's dopant one, its line width was like, I can't remember the number, but it was very broad.
Yeah.
It was broad.
This one looks narrow.
So I was expecting this to be narrow.
Okay.
Because the reason he saw the broadening was as an effect of the dopant, at least to my understanding of what he was doing.
Yes, I believe so.
And then the next slide, Dimitri. So this just like the slide two slides ago is photoluminescence, but in this one I was looking at the highest oscillator strength, which was HOMO to LUMO +1. So we see that a lot of the IR emissions in the intensity graph are gone, and the ranges are the same they were on the previous graphs. We see that a lot of the IR intensities are gone, so we can assume that was probably some interband interactions occurring. And we once again see the peak right around 3.3 eV for the band gap photoluminescence.
So for your intensity scale,
yep,
is that's not the log, that's linear?
The intensity scale is logged.
That is logged.
Assuming I read MATLAB correctly, yes.
So the x-axis for your intensity.
Yeah, the x-axis should be logarithmic.
So how many orders of magnitude is the IR peak bigger than the photoluminescence one?
About 3.
Huh.
Depends on how far exactly it goes past the end, but it looks like it's coming to the end.
Yeah, that is peculiar. Oh, wait. I think I know what that might be. So does your LUMO +1 and your LUMO have the same energy?
Yes.
So that just might be a bug in the code.
Okay.
Because there would be a 0 transition energy between them.
And that is basically right on the 0 mark.
Yeah. So that's what my guess is what that is.
Okay. Where did I put the mouse?
Okay. David, do you have more information to contribute?
Not unless someone has a question.
Okay, then let's thank David for interesting presentation that is matching very well what we did. Are there more questions? Levi is typing. He suggests to use.
Yeah, I'm looking at the link he sent me right now. I can't say I've thought about it, but
Waterfall is available in MATLAB. You do. I like GNU-plot very much, but it is also available in MATLAB. One can just type instead of mesh. One can type waterfall, and it will do the same. But then it will be three-dimensional picture, which takes effort to rotate and look from the necessary angle. It's interesting, but it will consume time.
Figure. There's the correct figure.
Aaron, do you? Oh, okay. There are concluding remarks from Aaron. So let's thank David once again. And a quick second.
Um,
24 megabytes for concluding remarks. That's cool.
Waterfall.
So, are you trying to check it in MATLAB right now?
Yeah, I am.
So be careful. Waterfall, then in brackets, the variable, and after variable, you may or may not need to put apostrophe. So depending on whether you transpose or not the matrix, it will write waterfall lines in different along different axes.
Okay.
Aaron, floor is will be yours in a few seconds. So the idea is that Aaron was involved in calculations on the manganese contributions to spectra and has publications on that, and Aaron is also involved in experiments, so he may summarize what has been found useful by Salim and David, and what needs to be improved, and what are the possible directions of improvements towards addressing open challenges from experiment. Aaron, floor is yours. And we do not hear you if you are speaking.
I should probably mute too.
Now it's okay.
Now, yeah, now we hear you.
So I guess I have two different contributions for this. So one part is just doing an extended calculation from Salim's model that he presented on earlier. And then the next part is experiments, and then how calculations can relate to observables that we've seen. So for the calculations aspect, you can go to the next slide. So previously on a couple of group meetings, I presented on exploring the, I guess, modules in VASP, which allowed to compute Bethe-Salpeter exciton spectra. So I didn't put in any of the details here, but essentially what I did is I just took one of the models that Salim's had for his dopant and computed spectra in our usual method, which is the IOA, or independent orbital approximation, and then compared it to what VASP provided from doing a Bethe-Salpeter equation, which is an extension of independent orbital, which includes Coulomb and exchange interactions. And those are compared in this figure. So red line is independent orbital, and the green line is Bethe-Salpeter. And so the main takeaway is that there's a consistent small redshift by about 0.2 eV. So that can be represented as like a binding energy of sorts. And then one thing we were hoping for was to see, or I guess a hypothesis is that including excitonic effects would boost the oscillator strengths of these DD transitions, since they're very localized. But just from this calculation alone, they're roughly the same order of magnitude. And so yeah, that's the main takeaway from this slide, is small redshift and not a lot of change in the dopant interactions. But I guess I do have one comment for for the perovskite transitions, it did seem that including the exciton or beta salpeter improved some of the higher energy transitions for the perovskite slab. I'm not exactly sure which orbitals and transitions they are, but it could be interesting to follow up on those. And so that's all I have to say about this calculation. So we can go to the, well, I guess, are there any questions? Because I was going to transition from this. No questions? Okay. So then another aspect on campus that investigates manganese dopants is the work we're doing in Eric Hobby's lab. And so essentially what we do is we synthesize the parent solution of these manganese dope perovskites, and this figure A and B is what Salim was showing earlier in his presentation. And so the reason they're interesting is that they have a very wide absorption. So this red line is the absorption onset, but their photoluminescence, they are dual emitters. So they give luminescence in the orange from this broad 600 nanometer peak, and they also give blue emission from the perovskite band gap. And so that's interesting with the parents itself, but we decided to apply the hobby group's competitive separations technique to these samples. So essentially we take the parent and then we do this so-called ultra density gradient centrifugation. So you can essentially size separate the nanocrystals. And then we can look at the role of size on the photophysical properties of these dual emitters. Next slide. And so that's what is summarized in this figure here. So panel A just shows the photoluminescence spectra for various different fractions or different sizes of NCs, and then panels B, C, and D summarize changes in quantum yields and photoluminescence maximum. So I guess just looking at B, we can see that, so on the left-hand side is small nanocrystals, so about 4 nanometers, and that the quantum yield for them increases up to a certain point, and then there's a pretty dramatic cutoff. And then for subsequent larger sizes, the quantum yields are fairly poor, or they keep decreasing. And we notice that where the sudden cutoff occurred, there was also changes in there were red shifts in the dopant PL. So normally they're around 605, but then once you get past this cutoff, they start to increase by up past 610, 615 nanometers. Then we also observed a curious effect where for the doped crystals, their bulk band gap is at 410 nanometers. So you'd expect that once you get to a large enough size, this blue line should cut off at 410. But we noticed that it's saturated below its bulk level. And to see if that was real, or if that was due to the dopants, or if the blue emitters showed some peculiar property, we just made a pure sample, so undoped crystals, and size separated them, and that's this purple line. And so you can see that it does saturate to where you would expect for the bulk band gap. And the main takeaway that we got is that this all seemed to happen around a certain cutoff point. So there must be some sort of, I don't know, physical reason for that. So next slide.
Question.
Oh, yes.
So panel B, quantum yield of all photoluminescence, 400 or 600?
Combined.
Okay. Yeah, thank you.
But it does, I don't present it here, but they do kind of follow each other.
Okay.
So you see improvements in both, and then lowering of both. And then this is photoluminescence decay trends. That's, I guess the main takeaway is that they follow the same cutoff trends as quantum yield and then the spectra. So once it hits a certain size, we see precipitous changes in lifetimes. And so that's just another clue that there's some sort of underlying mechanism for what's happening. Next slide. And so I was digging around in the literature, or I happened to come across one paper where they saw the same effect as the artificial confinement. So they basically just varied, they synthesized a bunch of samples, but varied the amount of manganese in them. So they went from like reasonable amounts to very excessive. And what they found is that once they increased to very excessive amounts of dopant, is that they started to see a blue shift in the exciton peak. And they had at their disposal high resolution TEM. And what they found is that for the very high dope samples, there were these essentially like micrograins within the nanocrystal. And they identified them as Ruddleson-Poplar defects. So in this B figure, if you look to the right, they have a color code of purple lines where they don't match up at the intersection. And so where green meets green, that's where they think that this Ruddleson-Poplar phase occurs. And then on the right is just some playing around with seeing if it would be possible to get some sort of lattice or to atomistically model these Ruddleson-Poplar defects in a big enough nanocrystal. And this is just initial attempts, but it does seem possible where if you follow from the bottom, you follow the big blue dots, which are cesium. They go through the crystal, and then once they hit this subphase, they take kind of a diagonal and then go vertical. So it kind of matches the lattice patterns found from those high resolution TEM. And I was just looking around in databases that these two different phases, they do have slightly different XRD patterns. So if we can get good enough XRD resolution, it could be possible to try to isolate the subphases within the crystals. And so I guess if this is actually what happens, I guess a good story for a paper would just be to have this optimized, but show that the HOMO and LUMO are just localized to a small portion of the crystal instead of being delocalized all around it. It would make for a good visual anyway. And we should also see an increase in the band gaps too. So this could be one route to providing a computational aspect. And I think that's my last slide.
Thank you much, Aaron, for this summary and directions. I thank Aaron. And the summary presentation is open for discussion and questions. So I do have thought and question, and I'm interested in your feedback. Can I interpret your story about this paper in the following way? So we can consider two structures, either in two styles of two streams of structures in both experiment and theory. One, when high concentration manganese dopants are randomly distributed along the crystal. And another option, when during the synthesis process, these high concentration manganese dopants form layers. So we will have two isomers, two families of isomers. One family with random distribution of dopants will have lower redshifted transition, and the self-aggregated spontaneous, the model with the same concentration of manganese, but with self-aggregated spontaneous formation of layers will be blue shifted.
It'll be slightly red shifted.
Wait. Why red shifted? If there are layers, they increase confinement and energies increase, so go to blue, right?
Oh, okay, yeah. So, yeah, the exciton or the nanocrystal peak.
Mm-hmm.
So at first I thought you meant, because it also, people attribute the redshift of the dopants due to aggregation of manganese too. That's what I thought you were saying at first.
Okay, I see. So there are multiple dimensions. There are optical properties of manganese itself that changes in aggregated and non-aggregated. And there are optical properties of the bands associated with intrinsic perovskite.
Mm-hmm.
Okay, so if someone or some of us wants to go after this direction, it means one needs two models or two families of models with layered arrangement of manganese and with random distribution of manganese.
Mm-hmm.
Okay. Someone is going to get food and depart. Oh, okay, I see. It is Levi. Okay. Have a safe walk to the food. Let's check if there are more questions, especially from the speakers. Salim, do you want to ask something to Aaron? Salim, your microphone.
I'm not sure what to ask.
Okay, that's
I'm not
fine.
sure what to ask, but I feel like it's amazing what Aaron just shared. I think that it's very amazing. I don't think I would understand everything, or even if I do understand what he explained, because he explained nicely, I'm not sure how, like, what to think after that. You know, it was really nice. So, and it's inspiring as well, as like work that can be done in the future, for sure. I'm not sure what to ask specifically. I understood what he was saying partly, I guess, but yeah, I'm not sure if there is a question that I can ask on this.
Okay, that's fine. David, do you have questions to Aaron or suggestions, or do you think you can create models like that? What is your feedback?
Now, if you really want me to, I can create models like that. It would take me time, but no, I have no questions.
So you just approve it as interesting material.
It is interesting.
Okay, yeah, thank you. Javed, did you want to ask something to Aaron?
No, I'm good now.
Okay, yeah, thank you. Fatima? Thank you. Fatima, do you have questions to Aaron?
Yes. I have one question. On the panel C, looks like there is a lattice mismatch. I'm wondering why. Like, is there any specific reason?
So this lattice mismatch is suspected to happen because you have two different crystal phases that are mean. So like in this model on the right, does my mouse doesn't show up? But I guess in the section where it says CS4 PbCl6, so that's one phase. And then where it meets the CSPbCl3, that's where they suspect the mismatch.
Okay, so CS4 PbCl6 is the mismatch, right?
Yes.
Okay.
David, would you like to add more in answering question by Fatima? I have a feeling you may add something unique.
I think Aaron explained it pretty well. I'm just sitting here and thinking at the moment about how the missing.
To me, it looks very much similar to your previous or current calculations and results, where you're considering two different phases, Rudelsman-Popper on one hand and Dion-Jacobson on the other. And they have the same stoichiometry, but they have like
Rudelsman-Popper slightly different stoichiometry.
And Dion-Jacobson has half phase mismatch in space, right?
So Dion-Jacobson does not have a mismatch. Rudelsman-Popper has the half phase.
Okay, yeah, thank you for correction. So it looks like if one wants to model this situation, one needs to bring in both Rudelsman-Popper and Dion-Jacobson phases into one simulation cell.
I would agree with what you're saying. And I'm just sitting and looking.
Yeah, Fatima, many thanks for setting up an inspiring question. It's an important direction of thinking.
Okay.
Yulun, do you have any comments or suggestions or questions?
Just curious, because for David's model, he needs some organic ligands to connect the perovskite, right? But it seems here the organic ligand is not necessary.
So in my model, the organic ligand acts as two of the anions, where here it looks like they have a divalent anion instead, I think. I'm trying to, what is this pink that I'm seeing in the model on the right in the CS4 PbCl6 region.
Well, that's manganese. That should be, yeah, replace
Okay.
PB and then.
Okay.
Okay, yeah, thank you, Ewan, for the question. So, do we have any other aspects for discussion right now? If no, let's thank all speakers and contributors to discussion once again. So next time, I think we will have meeting on the ruthenium catalyst, right? I will try my best to bring the undergraduate from the course who was doing it, but it could be very brief and is it what we planned for next meeting, right?
Yes.
On the schedule. Okay, and you did agree to show some results on the ruthenium catalyst, right?
Yes, just some basic electronic structures.
Okay, yes, very good. So, and we may invite Dr. Parent if he wants to join. Okay, then see you next week, same time, same link, and if we need to communicate one by one, we can continue it by email or set up another meeting. So let me suggest to finish the meeting and disconnect now.
Yes, thank you again, Dr. Killian.
Oh, thank you, Salim. Thank you much. It's very inspiring to have this stimulating discussions of several people with different interests. I think it helps to go forward.
Yes, I believe so too. Yes, it was really nice. It was really nice. I really enjoyed it too.
Okay.
Thank you.
Thank you.
All right. See you.
See you.
All right. Bye, everyone.
Bye. Yeah. Thank you, Masher.